Hi guys, it's Kate. This video is on how to determine whether points are coplanar. That is, if you're given a set of points, how can you determine if they lie in the same plane? Okay, let's take a look at this a little bit more closely. I'm not going to do a specific example, I'm just going to discuss this and look at the tools available to us. Say we're given 4 points. I'm going to name them P, Q, R, and S. Now, let's assume for just a moment that they do all lie in the same plane, and we'll see what happens. Let's create 3 vectors. Now, I've used these points to create these vectors, and they don't necessarily have to be these 3. You can pick any couple of pairs of the points, but I want 3 different vectors. Now, let's for a moment take A and B and cross them with each other. The cross product of A and B would be a vector. I've made it in blue here. And from the properties of the cross product, we know that this cross product would be perpendicular to the plane that A and B both lie in. Now C also happens to lie in that plane. So what do we know about the dot product between A cross B and C? Well, if these 3 vectors all lie in the same plane, C is also going to be perpendicular to A cross B, and so its dot product with A cross B is going to be 0. And this is a really important result. And in fact, this particular tool right here, this calculation, is called the Scalar Triple product. Now, let's think about it. What would that measure? What would the significance of that equation be if P, Q, R, and S were not in the same plane? It's definitely not going to give us 0, because that only happens if they are all lying in the same plane. But what is it going to give us instead? It's going to give us something non-zero, but what else is the significance of that number? I'm going to draw another example. Let's consider if P, Q, R, and S do not lie in the same plane. Now, any 3 points can lie in the same plane, so let's look at P, Q, and R first and construct the vector that goes from P to Q as well as the vector that goes from P to R. While those 2 can lie in the same plane, perhaps the vector from P to S does not. And maybe it looks something like this. Let's take a look at the scalar triple product and apply the definition of the dot product to this scalar triple product. Now let's see if we can make sense of the various pieces of this in the context of our drawing here. First, let's add in what A cross B is in this picture. And let's also add in theta. Remember that theta is the angle between A cross B and C. Now let's go left to right. The magnitude of A cross B. Well, in our unit on the cross product, we discovered that the magnitude of the cross product is actually the area of the parallelogram spanned by the 2 vectors that you're taking the cross product of. Let's draw that parallelogram in here. Then, what does it mean to get that area multiplied by the length of the vector C, right here, times cosine theta? Well, let's look at the fact that C and A cross B together create a teeny tiny right triangle, and I've correctly drawn this because C and A cross B are not always similar in length, but you can still sort of fill in this triangle in your mind, like so. A cross B is pointing straight up from the plane that vector A and B were in, and possibly C is not pointing in the same direction. So what happens when we're taking the length of C and multiplying it by cosine theta? Well, we're getting this length. I've made it a sort of see-through red here, but we're getting the length of this, the length of what is the height of what we call a parallelepiped spanned by A, B, and C. I'm going to fill in the other walls of this parallelepiped. I clearly did not space that out brilliantly, but you can at least see it now. The floor of the parallelepiped, this is basically a 3-dimensional parallelogram, and in fact parallelepipeds exist in higher dimensions as well, but you stop being able to see them. Well, the floor of this parallelepiped is the parallelogram that was spanned by A and B. And the area of that base is the magnitude of the cross product. And so if we take the magnitude of the cross product and we multiply it by c cosine theta, which is this length, this is the perpendicular height of this parallelepiped. And so what we get right here is the volume of the parallelepiped. Now you're absolutely right to say, oh, cosine theta could be positive or negative, so in order for us to really get strictly volume, we can add in absolute value signs around the cosine theta as well. That just comes into play depending on the angle it's making with A cross B, but it's not a huge issue. So again, what is the absolute value of the scalar triple product? Well, it is the area of the base, which is this parallelogram here spanned by A and B, times the perpendicular height, which is the length of C, times cosine theta, where theta is the angle between A cross B and the vector C. So this is the volume of a parallelepiped spanned by A, B, and C. You may be wondering if this is consistent with our previous result here, that this number would be 0 if they were coplanar, and in fact it is. Because what happens when P, Q, R, and S are all in the same plane? Well, that means that A, B, and C are all in the same plane, and so the parallelepiped would have no height. Sure, you could totally compute the magnitude of A cross B, but when it came time to do C times cosine theta, well, theta was always going to be, since it's the angle between the cross between A and B and the vector C, it's always going to be pi over 2. So cosine of theta will always be 0. And so if all of these points lie in the same plane, the parallelepiped is actually a two-dimensional object, doesn't have height, and it doesn't have volume. So that's why if P, Q, R, and S are coplanar, and their vectors A, B, and C are also coplanar, that's why A cross B dotted with C, the scalar triple product, is equal to 0. And if not, the absolute value of that scalar triple product is equal to the volume of the parallelepiped spanned by the three vectors A, B, and C made from the points P, Q, R, S, and the points are not coplanar.